Okay, good afternoon. Let us start our lecture. Okay, so yesterday we discussed, not yesterday, the last meeting, Tuesday, we talked about how to do the operation of events. We talked about sample space, which is a collection of all the sample points or the possible outcomes in an experiment. And then talk about event and how to do operations of events. All right. Also today we start something more useful in terms of computing the probabilities. That's how to count the number of ways that we can do things. All right. So basically there are two very important operations. One is multiplication rule. The other one is addition rule. And then based on those, and we have this permutation and combinations. So today we are going to talk about all this. All right. So first of all, about multiplication rule or principle. So basically, you can think of we try to do things. All right. In different stage. So the first stage or first operation, we have n1 ways to do it. And then for each of these ways, it's important that you have to make sure that you have this condition met. So each of these n1 ways, there are n2 ways to do things. All right. So you can think of it. So this is the operation 1, and this is operation 2. So there are, let's say there are 3 ways to do it. All right. And for each of these, we have, let's say, 2 ways to do it. So altogether, how many ways to do the operation 1 and operation 2 together will be 3 times 2. Or n1 times n2 in general. All right? So you just make sure that each of the ways that we do things in the operation 1, we have the same number of ways to do things in the second operation. So we can have an alternate statement. Instead of looking at how many ways to do it, we can look at possible outcomes in an experiment. Also, instead of ways to do things, is the number of possible outcomes. So in experiment 1, then we have this n1 possible outcomes, and then for each of these n1 outcomes in the experiment 1, we also have n2 outcomes in the experiment 2. So altogether, these 2 experiments together, we have n1 times n2 ways to do, n1 times n2 ways of outcomes. All right, so let's look at simple examples. So let's consider throwing a die and a coin, all right, together. So what are the possible outcomes? All right, so you can think of it, a die is experiment 1, and then coin is experiment 2. So for a coin, for a die, there are 6 possible outcomes. So n1 equal to 6 in this case. While the other one, all right, have 2 possible outcomes. And then for each of the outcomes, like 1, I can have head and tail for the coin. For 2, I also have head and tail. So they all have 2 possible outcomes. So basically multiplication is just a way to do addition. It simply means that we try to add 6 numbers. 6. So each of them are 2. All right. So if the die has the outcome 1, then we have this head and tail for the coin. Similarly, for the die having a result outcome which is 2, we also have 2 possible outcomes for the coin, head and tail. So we just add. All right. So 2. This is for the die have outcome 1. the die have outcome 2, we also have 2 possible outcomes. The die has outcome 3, we also have 2, 4, 2, 5, 2, 6, also 2. We add all this together. That's how we got 6 times 2. We have 6 times 2, or n1 plus n2. All right? So altogether, there are 12 possible outcomes. So therefore, the sample space of this experiment of throwing 1 die and 1 coin have 12 sample points. Okay, here's another example. So in a very small community, so there are 10 men, each of whom has each of these men has 3 sons. 3 sons. All right. So now we want to choose 1 man and his sons. Okay. So how many different choices do we have? All right. So you can think of it. Choose the father first. So it's the experiment 1, and there are 10 of them. So I can choose any one of these 10. So there are 10 possible outcomes. And for each of this father, they have each of them has 3 sons. So n2 equal to 3. Okay. So the possible ways or choices will be 10 times 3. Right? Seems quite straightforward. So let me ask you, suppose not all 10 men, okay, in fact there are these 2 questions. First one, the sons for 1 man is different from the sons from another man. Will it affect our choice? In the previous example, all right, we toss a die and a coin. All right, so the coin is head and tail. No matter what your outcome of your die, you will have head and tail. This one, you choose this father has 3 sons. Another man as father has another 3 sons. So is it okay that I multiply them 10 times 3? Is that okay? Yes? More. Okay, you see we are confused about multiplication. In fact, you think of it, if I choose A, okay, A to J man, choose A. He has 3 sons. So the choice for this A, all right, A, all right, man A. So have 3 sons, A1, A2, A3. All right, 3 choices for this particular man. Second man B, B1, B2, and B3. They are all different from this. The 3 sons from B is different from the 3 sons of A. But there's still 3 ways to do it. All right? So basically, it is 3 ways plus 3 ways and plus altogether there are 10 of them. So it's 10 times 3, so it's okay. Now if you understand that, then the next question will be easier to answer. What happens if 1 man does not have 3 sons, only 2 sons? How many ways to choose 1 man and 1 son? How many choices are there? How many possible ways to choose 1 man and 1 son? The son must be referring to the link to the father. So if one particular, let's say J, has only 2 sons, how many ways are there? So 3 plus 3 plus 3 until the man I is still 3. Man J only 2. So it's 3 plus, you have 9 times 3 plus 2. So basically it's addition. All right? So it's 29. All right? So we can multiply because each of the men in this example has 3 sons. They don't have to be the same 3 sons. All right? Each man has their own 3 sons. Yeah. Okay? Yeah. Okay. So this n1 times n2 ways to have the outcomes, number of outcomes, can be applied to more general situations for which we have k operations. So each operations has their own number of outcomes. All right. So altogether, it will be n1 times n2 times nk. So in order to use this one, make sure each of the ways. Okay, so for example, we start with first one have n1 ways. Then make sure that each of the n1 ways, there will be n2 ways to do the second operation. Then I multiply them together. Then, when you come to the third operations, make sure that for each of the combinations of n1 and n2, I have the same number of operations for the third operation, which is n3. Then I multiply them together. All right? So my point here is that, and the formula is so easy, just multiply them. Make sure that you know what are the conditions. The condition is that each of these operations must have the same number of the other operations in the following operations. All right, so this is a picture to show the idea. All right, so n1 ways to do things here, and n2 ways to do things, and all together. So in other words, this particular is one particular possible outcomes of all these k operations. So you can look at it. This is the outcomes of experiment. Just now is the operations, how to operate it. So let's look at this example. So now we have 5 digits, 1, 2, 5, 6, 9. 1, 2, 5, 6, 9. We want to know how many ways or how many choices. Or if we want to form even 3-digit numbers. All right? And each digit can only used once. Can only used once. All right? Now, how to do it? So of course, there are only 5 digits. We can try to list out all the possible ways to arrange these 5 digits and see how many of them are even numbers and also 3-digit numbers. But of course, we don't want to do it by brute force. We want to make it very simple and easy to compute the answer. So we start thinking of, okay, we have 3 boxes. The hundredths place, the tens place, and the ones place. 3 boxes. So we try to fill up these 3 boxes with these 5 digits. So we have 5, you can think of it, we have 5 balls. Ball 1, 1. Ball 2, 2. Ball 3, 5. With a number 5 written on it. Ball 4, the 4th ball, number 6, with a 6, number 6 on it, written on it. And then the last one is 9. Try to put them. Okay. So it's very simple. Can I arbitrarily fill up any of these 3 places? Why not? What's the problem? Because there are conditions. In fact, what are the conditions or constraints that don't allow us to arbitrarily put whatever we want to do? There are 3 conditions. All right? I already fixed one, the 3-digit number, so I treat it as 3 boxes. And what else? What are the conditions that I must fulfill? Huh? No conditions. Even number, use it once. 2 more conditions. In fact, there are 3. 3-digit number, even number, and also each digit can only use once. So life is like that. Once you have so many constraints, are they all equally in an equally status, or they are treated as equal? Or some have carry more weight. It's more important. We must fulfill that, meet that constraint first before we move on. So which one is more important? 3 of them. 3-digit number, even number, and use only once. Even number. Or any other answers? even numbers. Why? Because the other, okay, 3-digit number, that means 3 boxes. We have not come to 3 boxes yet, or the 3 places. We only look at form an even number. We must meet that first, all right? So, how to meet it? That means we must look at the ones place, the unit place. Okay, this is hundreds, this is the tens, this is the ones, all right? So ones place, we must put an even digit, all right? So look at our possible digits, 1, 2, 5, 6, 9. There are 2 of them. So in other words, I can only fill this ones place with 2 choices. So n1 equal to 2. Okay, so that is the first most important criteria that we met, even number. We meet that first. All right? So n1 equal to 2. Why I have to do that? Now, if you don't fill up the ones place first, okay, you think of it, start from the hundreds, 3-digit numbers. I can fill in any one of these 5 digits. So 1, 2, 5, 6, 9, I can put it there. So it's 5 choices. But once you fill up that, all right, let's say, so there are 5 choices, all right? If I fill up a 1 in the hundreds place, all right, then, okay, I can fill up the tens and then the ones. But it depends on whether you have used the 2 and 6 digit in filling up these 2 places. Once you fill up, then the choice that you can put in the 1 places will be different. So it makes things more complicated to work on. I will not say that you can't do it. Yes, you can do it, but it's very complicated. So we try to meet the most crucial condition first. So we try to make it even number. So put a 2 or 6 there. So after that, all right, then so now I left with 2 places or 2 boxes that I have to fill up. So which should I fill up first? Hundreds place or the tens place? So hundreds place, tens place, doesn't matter. 3 choices, right? So you must be able to answer, right? Which one? So if you think that it doesn't make no difference, then it doesn't matter. Otherwise, you have to fill in hundreds place. Now, hundreds place is important because it's one of the criteria, 3-digit numbers. But after you fill up the ones place, the remaining set, okay, it doesn't matter whether you take a 2 or you took a 6. The remaining 4 digits can be used to fill up the hundreds place. All right, so it doesn't matter. Even if you don't fill hundreds place, you fill in the tens place, okay, so then use 2 digits. The remaining set of digits still able for you to fill up a digit, the hundreds place. The only problems arise when you have a 0 there. Then you have to be careful. All right? So in this case, it doesn't matter whether you fill the hundreds place or the tens place. Now comes another condition. You can only use the digit ones. So once you fill up the ones place in stage 1, then in the second one, you only left with 4 digits. All right? So if you fill up this, then there are only 4. So, and after you fill up this one, there are only 3 digits left. So it will be 4 times 3 times 2. The notes here I fill up the tens place first, and then followed by the hundreds place. All right? It doesn't matter. So the answer is 24. So this one is straightforward. We have 10 multiple choices questions. So it's like we have 10 experiments. Each one, we have four outcomes, all right, 4 possible answers. So how many answers are there? So n1 equal to 4, n2 equal to 4, up to n10 equal to 4. Because we have 10 multiple choice questions. Each multiple choice questions considered as one experiment. And there are 4 possible outcomes because there are 4 possible answers. So multiply them together, that will give you the number of possible ways to answer it. All right? You know how big the number is? It's, yes, 1 million. 1 million, all right? So think of it, if you just guess in a multiple choice questions test, 10 of them, the chance that you got all correct is 1 out of smaller than 1 out of 1 million, right? So the moral of the story, study lah. So don't guess. I know, sure, 4 answers, I got the correct one. I answered correctly each question. Then I got all correct. I got an A+, right? Okay. Now, how about, among all cases, how many of them are, all answers are wrong? All answers are wrong and all answers are correct. They are not, okay. Are they complement of each other? Are 2 events. All answers correct, all answers are wrong. Are they complement of each other? Is there any in between? Of course, there is something in between. Hey, I can answer 1 correct, the rest wrong. 2 correct, the rest wrong. Right? So these 2 are not complement of each other. All correct and all wrong. But there are some correct, some wrong. Okay, for the 10 answers that I choose, maybe some correct, some wrong. So they're not complement of each other. So how to do it? So same thing lah. So first question, wrong. How many choices will give you wrong answers? 3 out of 4. So we just choose 3. So it's just 3 times 3 times 3. So it's 3 to the power 10. What's it? Is it mine? Okay, so it's not that bad. 60,000. So if you guess, you still have, got 0 marks chance. It's only 60,000, right? Out of 1 million. So it's not that easy to get 0 mark, in other words. All right. But yeah, there's something called luck, right? If you're so unlucky, all answers wrong, so you got 0 marks. Otherwise, you may have able to get at least 1 answer correct. So, okay. I think I skipped this example. You can read it yourself. This one also. Okay, example 5. Sorry, still come back to this digit thing, form numbers. Again, even 3-digit numbers. All right? 1, 2, 5, 6, 7, 8. Each digit can be used once. And if no restriction on how many times we can use. All right. So this one is similar to just now the example 2 that we discussed, except the B part, no restriction. So we remove 1 restriction, that means the digits can be used more than once. All right. So for the first one is 5. Okay. So we have to fill up the ones place. All right. And there are 3 choices. So 3 choices. So n1 equals 3. We must do the most crucial condition. Even number is very important. The next one is the 3-digit number as well as use it once. So the 3-digit. So after that, we fill up the ones place. We have 5 digits left. So we have 5 possible. That means for each of the number digit that you used here for the 1. This is for the number of ways for 1 place. Then you left with 5 digits. 5 digits. So you can pick one out of these 5 to fill up the 100th place. After you fill up these 2, then the 10th place left with only 4 digits. So multiply them together. You have to understand why we multiply. Because we fill up the ones place first. There are 3 choices. 2, 6, and 8. After that, you use 1 digit. So you look at now the remaining digits. There are 5 of them. You can use any of these 5. Once you fill up the ones place, use these 5 to fill up either the 100th place or the 10th place. All right? So there are 5 choices. Then, left with 4 digits, fill up the remaining place. Okay, how about use for more than once? That means you can use anytime you want. But you still need an even number. You just remove the condition that used once. You still need 3-digit number. 2 conditions. Even number, 3-digit number. So the even number is most crucial. Fill up that first. Meet that criteria first. So we fill up the ones place first. There are 3 choices. For each of these choices, I left with still 6 digits because I can reuse the digit that I used for the ones place. Okay, so I have 6 digits. So fill up the hundreds place. After I fill the hundreds place, I still have 6 digits because I can reuse the digits again. So it's 6 times 6 times 3. All right? Okay, this one's straightforward. This is interesting. Example 7. All right? Now, I have 4 boys and 5 girls sit in a row. And if the boys and girls have to sit in alternate seats, all right? So, a boy here, okay, girl, boy, girl, boy, girl, boy, girl. So far, so good. Then, I still have 1 girl, I have to put her somewhere. I cannot put it here. I have 5 girls, right? Then that would not met the criteria, say, alternate seat. So where do I put the girl? Cannot put here, here, here. I can only put it here. That's the only way that I can arrange 4 boys and 5 girls in alternate seats. All right? Okay, this is the frame or the arrangement. But now the question is, how do I going to fill up all this? So it's easy. I have 5 girls, okay? So A, B, C, D, E to represent these girls. So I can choose these 5 girls, one of them put it in this seat. Then after that, for each of these choice, how many choice I can put a boy next to her? So if the boys are called alpha, beta, gamma, delta, I choose one out of these 4 boys into the second place, second seat. So altogether, 5 times 4 times 4, 5 choice for this one. For each of these 5 choices, I have 4 choices for the boys, and then this one, the remaining 4 girls, and so on. So altogether, there are 2,880 ways to sit these 4 boys and 5 girls in alternate seat. By the way, this notation, this is not 5 exclamation mark. All right? Yes, yeah, it's written like that, but in mathematics it's called 5 factorial. 5 factorial means that it is 5 times a number, a factor, one less than it, continued times another factor until you reach 1. That is 5 factorial. So n factorial is n times n minus 1 up to 1. All right? Now here's the question. So what happens if I have 5 boys and 5 girls? So you ask yourself, so how many ways that you can, okay, first of all, we do it in step. Before we assign the boys and girls, let's arrange such that it meets the criteria that the boys and girls are sit in alternate seat. So this is already 4 boys and 5 girls. So, 4 boys and 5 girls. So now I have an extra boy. So I can put it here or put it here, right? Correct? Okay, so in other words, what I mean is that you can put it here. So this is one arrangement to meet the criteria that the boys and girls are sit in alternate seat. This is our arrangement. All right? Another arrangement is to put the boys, the 5th boy here. So this is another arrangement. Right? Are they the same? They're not the same. They're not the same. Right? So, why they're not the same? Obviously, this one a girl start from the left for this arrangement. While this arrangement, the boy start from the left. So there are two arrangements. So you have to figure out how many ways that you can assign the boys and girls in each of these two arrangements. All right? But in fact, how many ways that we can sit it here? What's the answer? Same as the previous one, 2880. Why? Because after you fill up the ninth place, this seat, you must sit the boy there. Only one boy left must sit there. So it's the same thing, all right? So if you really want to compute it, you just have to multiply by, okay, sorry. So it's 5. Oh. So it's okay, it's not 2880. Sorry, my apology. Okay, it is 5, and this one is 5, 4, and so on. It's just multiply them. All right? Okay. So, naturally, I add one boy to this part A, to this question. Just now I start with 4 boys and 5 girls. So I add 1 boy, 5 boys, and 5 girls. So I still can calculate it. So let me ask you, how many ways can I sit? All right? 4 boys and 6 girls in alternate seat. 4 boys and 6 girls. So I add 1 girl to the 5 girls. So 6 girls. And the answer is no. Impossible. Right? You go back to this arrangement. Where do you going to put the girl? No matter how you put it, they must sit next to a girl. So there's no way that they can sit in alternate seat. All right? Okay. Addition principle. So, addition principle is sort of like a special case, not special case, but more general case, in fact, of the multiplication rule. Because multiplication rule, you need to have each of the operations or experiment, for each outcomes in the first experiment, you must have the same number of outcomes in the second experiment. While addition, you are not talking about different, you are talking about just one experiment, okay? One experiment. But there are one experiment, all right? But there are a few ways to do it. Each way, how do I use the word? Here I use procedure, all right? Okay, let me put it this way, make it simple. Suppose I want to go from A to B, very simple, A to B. I can take MRT train. I can take bus, right? So there are two different modes of transport. And the MRT train, there are so many lines, right? I can go to the north and then come down to, all right, there's a northeast line, north-south line, and east-west line, and northeast line, and circle line. So many lines, all right? So even for this particular mode of transport, there are so many choices, all right? Buses, even more, so many routes, all right? But, all right, if I want to get from A to B, although I have so many choices, all right, but I can only take one, for example. Take one. So either I decide, okay, I better take a MRT train. So I decide whether I should, maybe let me put more, I don't know whether you are familiar. Let's say from Kent to Bishan, right? Bishan. I can take MRT Circle Line, all right, direct. I can take to the other line to the city and then transfer to another line and then come back, all right? Maybe go to World Trade Center, all right? What's the stop for World Trade Center? Is it World Trade Center? And then come back, or take the Circle Line, come back. So what I mean is that there are many even for MRT train, you have many ways to do it. Bus also. I don't know how to take bus from Bishan to Kent Ridge. All right, but there must be more than one. You can transfer. So my point is, you decide on your route, and then the route, there are many routes. One is maybe take different line of train or different route of bus. So, but you can only take one. All right. So in that case, I have to add up all this together. So it's N1 plus N2, N1 plus N2. So we are talking about only one operation, but there are many modes of getting this outcome. Taking train or taking bus, all right? So how many possible train lines, how many possible routes of bus, then you just add them together. So in general, if you have k of them, then you just add up all the k of them. Okay, I would say that to differentiate multiplication principle and addition principle, if you think of it like this, when you write a program, write a do loop, right? If it's nest, one nest in another one, so how many operations altogether will be a multiplication? But if it is not nest, not one nested in other, then you may need an addition rule, all right? Okay, here is an example. We have just mentioned it, all right? Okay, wow. This one, we need addition rule. Why? Because there's a 0 there. It makes life so much harder, complicated. You see, it's still even 3-digit number and use only once. 6 digits, but there's 0 up. 0 is very, very special in these questions because it helps us to meet two, or when we consider 0, it affects, where we put this 0, affects two conditions. What are these two conditions? Even number. And what's the second one? 3-digit number. Because you cannot put a 0 in the hundreds place. In general, right? 001 is not 3-digit number. 001 is one digit. All right, so you cannot put a 0 in the hundreds place. So like 012 is 12. It's not 000 and 1 tens and 2. All right, so it's not a 3-digit number if you put a 0 in the hundreds place. So in that case, we still have this 3, All right? So which one is more important? It seems that now suddenly the 3-digit number becomes the most important or crucial condition that you have to meet first. So we consider, all right? All right. Okay. We, as I said, because this is very important, so you have to look at this 0 because 0 affects whether it's a 3-digit number, whether it's an even number. So now we put 0 in the ones place. Because once we put the 0 in the ones place, then I don't have to worry about it. Automatically, the rest will meet the 3-digit number conditions. Because I don't have to worry, I will not put a 0 in the hundreds place. All right, so I start with 0 used in the ones place. Therefore, the remaining 5, I can put it in the hundreds place, and then in the remaining 4 in the tens place. So altogether, there are 20 ways to do it with 0 in the ones place. All right? Okay, so now, if the 0 is not in the ones place, all right, then, okay, remember now you have a 0 there. Okay, you don't put a 0 in the ones place. So we need an even number. So now you need an even number. So I have to choose from the remaining, all right, 2 or 6 in the ones place. Because now 0 is not in the ones place. So I have to meet this even number conditions. So I have to put either 4 or 6. So there are 2 choices in the ones place. After I fill up that, I still have 5 digits left, all right? But I cannot put a 0 in the hundreds place. I must, okay, so here there's some difference. The ones place, the tens place, and the hundreds place. Because I cannot put a zeros here, ones place. I already consider the case 0 is not here. So I must put a 4, a 2, or 6. So there are 2 ways to do it. All right, after that, so now there's difference. I have in my remaining 5 digits, all right, I have to put here first. Why? Because I make sure that 0 is not there. So in other words, besides the 1 I put in the ones place, which is either 2 or 6, I also put aside a 0. So I left with only 4 digits to fill up the hundreds place. I need to fill up the hundreds place first. So 4 ways. Why 4? Excluding the number, the digit you use to fill up the ones place and the 0. After that, I really left with 4 digits. So there are 4 ways to fill up this. All right? So that's 32. And now, I have 2 scenarios. One is with 0 in the ones place. The other is with 0 not in the ones place. So both will form of 3. Both represent the number of ways to form of 3-digit even numbers. I put them together. All right? So I have to add them together. So this is the number of 3-digit even numbers formed. Okay, so this one is similar to the previous one. Use only one with even number, 3-digit numbers. All right. Okay. I think we are still referring to 3-digit number. That is greater than 420. Okay, so the part 1 is quite straightforward. I mean, not straightforward, but we have discussed something similar. So let's go to part 2. All right, part 2. All right, now part 2. What is the part 2? Part 2 is no more even number. Let me repeat the question again. And no more even numbers. That is, it's only saying that a number greater than 420. 420. Greater than 420. Now, greater than 420. So, greater than 420 means that the hundredths place must be 4, 5, or 6. But 4 is not the same as 5 and 6, because if you put a 5 in the hundredths place, the rest of the 2 numbers, the rest of the 2 digits, the 2 places, you can fill up any numbers. The number formed will be bigger than 420. But for 4, it's different. For 4, once you fill 4, then the tens place must be greater or equal to 2. So in other words, you cannot choose a digit less than 2. All right. Okay? So we consider 4. All right? And then suppose it's a 2. It's a 2. Then once you fill up the hundreds and the tens place, we live with only 4 digits to fill up. So that is the number of ways that we can fill up a number, which is 4, 2, and then any digits. 4, 2, and any digits taken from the rest or the remaining digits. Why I have to consider that? Because if I fill up, okay, a 2, then the remaining digits basically is what are these? 4, 5, 1, 2, 3, 4, 5, 6, right? Or 0, there's a 0. All right? Yes. So there are 4 choices left. But if you fill up 3 there, I can once you put one of these, then the number of digits left that you can fill up, including the 2, you can fill up there. Right? So therefore, the number of choices are different. So that's why we have to consider separately. All right. If you put a 2 in the 10th place, you only have 4 choices left. But if you fill up the 10th place with digits 3, 5, and 6, it doesn't matter what you choose for the 1st place from the remaining set of digits. They're always greater than 420. So there are 5 choices. All right. Then for the case where you put 5 or 6 in the 100th place, all right, so fill up the 100th place first. This is referring to the 100th place. Then you fill up the 10th place, any numbers you want. All right, even 0 can be put there, and then left with 5. So multiply, this is the 10th place, this is the 1st place. So altogether, that's 60. And each of all these are different. So I have to add them up to get the answer. All right, so altogether 79. Okay, part B. What is part B? We list the conditions that digits can only be used once. Now I can use more than once. That means I can repeat. So how many form? How many are odd? How many are even? And how many are greater than 420? So how many can form? So I just make sure that, so now left with only one condition that I have to make, a 3-digit number. All right. So the 100th place, I can fill up 6 ways because I have 7 digits, excluding 0. I have 6 choices to put it here. And this one, 7, and this one, 7. So multiply them. Odd number. So now I have one condition, odd. I mean extra condition, odd number. So I fill up the 1's place first. All right. After I fill up the 1's place, all right, then I fill up the 100th place. All right. For 100th place, I have 6 digits only, excluding the 0. I can reuse the 1's place digits. So altogether, I have 6 digits that I can use to fill up the 100th place. Then the remaining 10th place, you fill up any number any digit that you want. All right? So there are 7 choices because you can use it more than once. Use the digits more than once. So even number, then this is the 1's place, fill up first, then the 100th place. It makes life easy in this case because the digits can be reused. So it's much easier to work with. All right? So you only consider, first of all, odd or even. That's most crucial. The next one is make sure there is a 3-digit number, excluding 0 in the 100th place. Then the rest are quite straightforward. 420, great, 420. So it's the same thing, all right? Except that this one, all right? So we're excluding 0, so we're including 0, and so on. So it's the same as before. Except that, remember, you can use the digits more than once. So, after all, we have all these possible scenarios, outcomes, number of outcomes, and altogether there's 132 ways to form a digit bigger than 420. Okay, so permutations. All right. If I have 3 objects, A, B, C, I want to arrange them. How many ways to arrange it? So it looks as if I have 3 boxes. I take out one, for example, A, I put it here. Take another one, C, and then B. So this is one arrangement. This is box 1, box 2, and box 3 in that order. So that's one arrangement. So our question is, how many are there? How many ways that we can arrange these 3 objects? All right. So it's very simple. Just learn it. Apply the multiplication rule. How many choices we can have to fill up the box 1? 3 choices. Because we have 3 objects here. Next, after you fill up this one, arrangement, so that means you cannot reuse the object again. All right? So in this case, then you left with the other 2 objects. So there are 2 ways to do it. For any one that you put here, there are 2 other choices that you can put in the second boxes. And finally, you have 1. So multiply them together. So that is how you do it. So there are altogether 6 ways. In fact, these are the 6 ways to arrange 3 objects, A, B, C. A, B, C. Simple, right? Then asked, how many ways that you can arrange these 3 objects? I just take 2, only 2. 2 out of these 3 to arrange them. How many ways that I can arrange them? Simple. So now instead of 3 boxes, I have 2 boxes only. First one, 3 objects, right? So there are 3 choices. And for each of these, we have 2 choices. So again, we have 6 ways to arrange 2 objects taken from these 3 objects. You can think of it like this. All right? Because the remaining one must put in the third box. So that's why it seems that there are the same number of ways to arrange 3 objects. Or to arrange 2 objects out of these 3 objects. The same number of ways. All right. Of course, then I can expand it to 4. If I have 4 objects, all right, arrange them. How many ways that I can arrange them? So it's 4 times 3 times 2 times 1. So it's 24. Or 4 factorial. How about arrange 2 out of 4 objects? Take 2 and arrange them. So it will be 4 times 3. So this time it's only 12. 12. All right, just take it 2. All right. Because you fill up the first with 4 choices, and for each of these 4 choices, there are 3 choices that you can fill up for the second box. All right? So to fill up and to arrange and I have to specify distinct objects. These objects can be differentiated. You can tell the difference. All right? So we treat it as n distinct objects. So the way that we arrange it will be n factorial. All right? A little bit about mathematics. N factorial. So 1 factorial means that you have 1 object. How to arrange them? 1 way to arrange them. You just have 1 way. Now the problem is, if I have no object, what does 0 factorial mean? We cannot treat it how many ways that we can arrange it. So mathematically, 0 factorial is defined as 1. You will see why is that so later on. But it's in terms of mathematics. So 0 factorial is 1. So make sure that you differentiate that. 0 in the denominator of a fraction is undefined. 0 factorial in the denominator is okay because it's defined as 1. All right? Okay, how about if I have only R of them? So, think of it, you have R box. First one, you have n choices. Second one, because you pick up 1, left with n minus 1. All right? Then the second one, n minus 2. If we have R boxes here, what is the number of remaining objects that I can fill up this box? So, you look at the pattern. n minus 1. The second box is n minus 1. The third box is n minus 2. This R box will be n minus bracket R minus 1. All right? This is the number of remaining objects that you can fill up. So the total number of possible ways to arrange these R objects out of N objects, all right, is N times N minus 1 up to N minus R, N minus bracket R minus 1. All right? Now, here is the magic. So, I don't want to write down this one every time now. So, what's the next one now? This in fact just N minus R plus 1, right? If I simplified it. So the next one will be N minus R, 1 less than it, N minus R minus 1, N minus R minus 2, up to 1. If I write it like that, this whole thing is called what? What do we call it? N factorial, right? But I cannot just multiply this one, it's different. So now I have divided by N minus R up to 1. So what do I call this part? N minus 1 times N minus R minus 1 and so on. This is N minus R factorial. N minus R, N minus R minus 1, and so on. So this part is N minus R factorial. So this is written as N factorial divided by N minus R factorial. All right? It simply means that it's N times N minus 1 up to N minus R plus 1. That is the number of ways to arrange R objects, distinct objects, out of N objects. All right? Okay, so in particular, if R equal to 1, how many ways we can arrange it? So it's N factorial over N minus 1 factorial, so it's N. Is it reasonable? You have N objects. You just try to take one object and arrange them. How many ways that you can arrange them? Take one out. That is the one, right? You don't have arrangement because you only have one object, but you have a choice to pick it, which one. So it's N choices. So it's N. All right? How about if I take all N objects and arrange them? All right? That means R equal to N. R equal to N. Then it becomes N factorial over N minus N factorial. Yeah, this is the one. All right? So the denominator is 0 factorial. All right? So now we understand, we just argue. Choose N objects, arrange them. How many ways? N factorial. All right? So you make sure that this equal to N factorial. How can this equal to N factorial? So the 0 factorial must be 1. Otherwise, the left-hand side will not equal to the right-hand side. Okay, so we define 0 factorial as 1. Otherwise, it's not consistent. All right? Okay, so here are some examples. Find the number of all possible 4-letter code words, which all letters are different. So in other words, we have a set of 26 objects. They are all distinct. All right? And then we just pick 4 of them, arrange them. How many ways that we can arrange them? So R equal to 4 and N equal to 26. So the answer is 358,800. Yeah. Okay. Nowadays, computer is so abundant. Computer power is so abundant. In the old days, if let's say, if I have 100 objects, I want to choose 3 of them and arrange them. How many ways we do it? So take out the calculator. Oh, have this factorial thing. So press 100 factorial. 100 factorial is a huge, huge number. Your calculator may not able to calculate it. So my point is, don't blindly apply. Oh, okay. This one's supposed to be equal to what? 100 factorial over 100 minus 3 factorial. Or in other words, is 100 factorial over 97 factorial. All right? My point is, don't try to evaluate 100 factorial. You cannot get, may not able to get 100 factorial. Maybe nowadays the calculator is more advanced that you can get 100 factorial. All right? But if you pay attention, this simply means that it's 100 times 99 times 98, which Even without calculator, you're able to do it. What? You don't know how to multiply 99 to 98? All right. So that's my point. Sometimes you don't have to apply, use your brain. Don't just apply mechanically, 100 factorial over 97 factorial. I need to calculate 100 factorial. No need, because 100 factorial divided by 97 factorial, you cancel a lot of the factors. You only left with 3 factors, 100, 99, and 98. Okay. This one, 20 horses in a race, and how many ways that you can arrange first, second, and the third spaces. So here we just select 3 horses out of these 20 and arrange them in the first, second, and third. So it is R equal to 3 and N equal to 20. All right, and then try to arrange them. So that is how you got it. Okay, example 3. So now we have 6 persons lined up to get on a bus. How many ways can we can arrange them? So what is N? N equals 6. What is R? Also 6, right? Because we did not select a subset of it. We consider all the 6 people. So it's P66. Okay? So the first one is like that. All right? So it's 6 factorial. Okay. The second one, if 3 persons insist on following each other, how many ways can these 6 persons line up? Wow. Headache, huh? 3 persons cannot, insist to line up together. All right, how to do it? In fact, if you think about it, they insist to be together. We treat it as one object. All right. So the remaining 3 other persons as 3 distinct objects. So in other words, let's make it like this. Suppose it's A, B, C, D, E, F, 6 persons. All right, and then we. Assuming that, okay, this is the group that you want to be together, line up together. Yeah, friends, right? So you have to talk. So you have to keep insisting they have to line up together. So I put this as one big object. Let me call it capital A. So now I just have to arrange these 4 objects. Big A, D, E, and F. Arrange them. So 4 objects, arranged 4 objects. All right. So one particular arrangement may be like this: D, A, F, E, for example. This is an arrangement of these 4 objects. But these 3 insist they follow each other, but they did not say that. Okay, I must be the first one. The lowercase a must be the first one. Lowercase b must be the second one. They can arrange among themselves. So you ask yourself, how many ways you can arrange this big A? Within the big A, how many ways that you can arrange them? All right? So I can now expand this big A into how many ways? So there are 3 of them inside this object big A. So there's altogether 3 factorial. All right? So in other words, it will be choose 4 and then choose 3. This one, 4, referring to this 4. Then this one, for each of the choice here, which arrangement here, I have to expand this A into, for example, D, A, B, C, E, F, E, or D, A, C, B, F, E. All right, all these are A. I just expand it. So the answer for this is, all right, 24 times 6. So it's 144. 144. Okay. Third part. Now, 2, they're not friends. So they insist not to sit together, queue up together, follow each other, refuse to follow each other. So the trick that we just doesn't work here. So what to do? So you just think the other way. Instead of finding how many ways that they refuse. I mean, these two will not be together. So think of it. I find how many ways that these two are together. Then subtract it from the total ways. Because for any of this arrangement, either they are together, these two persons together, or they are not together. So we are asked to find how many ways not together. So we find how many ways they are together and subtract from the total. So that's the idea. So how many ways that we can find them? So it's easy. So this is how many ways? All right. This arrangement within the two persons. All right. Because there are 5 objects, 6 persons. So let's say A, B, C, D, E, F. Let's say this one, now we call it B, okay? So this is one object, but you can permute within this object. So there are 5 objects we can permute. So it's 5 factorial times 2 factorial. Then total is 720. So subtract from 720, so 480. So the point is, right? Together. Insist that they queue up together, follow each other. Then you just group them as one big object. So treat it as one big object or one object. Try to permute with others. But after that, you also you can also permute within this big object. So you multiply the ways. All right? But not refuse to follow each other, then you just find the opposite. Find how many ways that we can put them together, these two persons together, and then subtract from the total number of ways. Okay, how about if we arrange n distinct objects in a circle? In a circle, how many ways? All right. Now, for a circle, unless you put in the direction, all right, north, south, east, west. Otherwise, your arrangement will be, all right, you go for a party, 4 persons sit together. What your interest is only who sit next on your right, who sit next on your left. So in other words, what I'm trying to tell you is that this A, B, C, D is the same as A, B, C, D, right? Because on the right-hand side of A is always D. On the left-hand side is B. So these two arrangements is considered the same arrangement if they sit in a circle. Sit in a circle, all right? Because in a circle, there are no left and right. Left end and right end, all right? Not in a row, in a circle. So the position is relative. Who sit next to you? Who is on the left? Who is on the right? So this A, B, C, D that I wrote down here, and the other one, they are considered as it's the same arrangement, same order, same arrangement. So how many of them are considered the same? Altogether, all right, this one, you can see that. If you arrange in a row, these are 4 different arrangements. But if you arrange it in circle, A, B, C, D. Okay? So this one, okay, start with B, C, D, A. This one, C, D, A, B. You see, basically they are the same thing. You just shift around, turn it 90 degree or 180 degree or 270 degree. So they are all the same. So we divide by the number of objects. So it's n minus 1 factorial. Right. Usually we will not have such questions, but you have to remember, once you put it in a circle, there are no more left end and right end. So it becomes a circle. So the arrangement will be the same if the relative positions are the same. All right, so example, straightforward. All right. Now, so what happens? What happens? Now here's another question. What happens if not all n objects are distinct? All right, suppose n one of them of the same kind. You cannot tell the difference. So maybe let me, a simple example. Arrange A, B, C, D. All right? Letters A, B, C, D. They're the same. All right? Okay. Maybe A, B, 1, 2. 4 objects, A, B, 1, 2. If you arrange them, then you have 4 factorial arrangement. All right? But let's say now I cannot tell whether they are A and B, but they are just alphabets, A. This one just numeric and numbers, okay? Numbers. So I cannot tell the difference between them. All right? So they are not distinct. All the 4 are not distinct. Okay? 2 of them are alphabets, 2 of them are numeric. So how many ways can we arrange it? So it's very simple. This one, we have 24 ways to arrange this one. Let's say this one is a particular one, right? This is another way. This is a third way, all right? And this is the 4th way. 5th way, A2, B1, all right? But now you look at this 4, there are 4 different arrangements. But if now I replace all the B's by A's, then this becomes AA, and replace the 2 by 1s, this becomes 1, 1. So all becomes AA, 1, 1 for this 4. For this 4. All right? For this 4. So they will treat as 1. So in other words, what we have to do is to, assuming that they're distinct, okay, you have n objects, or consider they're distinct, so they're n factorial arrangement. But this n factorial arrangement, once you don't have distinct objects, then you have to divide it. Now in this case, okay, it's like this. Look at the alphabets with 2 of them, A and B. If you treat it as differently, I have so many arrangements. But if you treat it as the same, then this, all right, and this, AB12 and BA12, this arrangement, these 2 arrangements is considered the same if you replace the B by A. So it's AA12 and AA12 for the second one. So how many of such things that are considered the same? You just divide by 2. In other words, you just have to see how many ways that you can permute this AB, and there are only 2 ways. All right. Similarly, for the numeric, you have only 2, 1 and 2. So you see how many ways that you can permute them. So you just have to divide the number of ways. All right. This is the distinct one, and then divide by n1 factorial. This is the number of ways that you permute the n1 in distinct objects. If you treat it as distinct, then you don't have to divide it. But once you treat the same, then all becomes 1. So that's why you have to divide by 1. So divide by n1 factorial. All right. Because all this n1 factorial arrangement is considered as the same. My example is not very good, but let's look at this one. All right, there are 3, 4, and 2 balls, bob. All right, and fit into the 9 sockets. So how many arrangements are there? Now these light bulbs they are different colors. So we start with assuming that you can label these light bulbs 1 to 9. So 9 light bulbs. Arrange them. So there are 9 factorial ways to arrange them. Let's say 1, 2, 3 are red, right? Number 1, 2, and 3 light bulbs are red color. So the arrangement with this 1, 2, 3 or 2, 1, 3 or 1, 3, 1, 2, all these I will treat it as red, red, red. So how many of them? 3 factorial of them are considered as 1. So we have to divide it by 3 factorial. Similarly, you have to also consider the other 4 yellow. The numbers that you label yellow now becomes 1, only yellow color. So you divide by 4 factorial. So altogether, it's 9 factorial, divided by 3 factorial, 4 factorial, and 2 factorial. All right? So that's the number of ways to do it. All right? Oh, combinations. This is most important way of doing counting. Disregard the order. All right? So that's called combination. These are some of the notation that we use to mean that we select R objects out of N objects. Now you select, you don't have to arrange them. So it's not a permutation. All right? So this means that you choose R objects out of N objects. Choose R objects out of N objects, or sometimes write it in this way. These two are more popular ways to represent a combination. So, how many ways that we can arrange them? This is the answer. N factorial over N minus R factorial over R factorial. How to get that? Remember, when we permute R objects out of N objects. Okay? Oh, what is it? It is this one, right? And it is N factorial over N minus R factorial, right? Okay? So in other words, basically, this number that I just written down means that it's a number of ways that you take out R objects from the N objects and then arrange them. So now, I said, forget about the arrangement. You don't need to care about the orders. You just select R objects out of N objects. So all this, so many arrangements are treated as one. So I have to divide how many ways that you can arrange these R objects that I select. So divide this by R factorial. All right? R factorial is the number of ways that you arrange the R objects. Okay, let me repeat it again. You have N objects here, right? You take out R objects. So the remaining one here, you take out this object, arrange them. And how many ways that you can arrange them? N factorial over N minus R factorial. It's the number of arrangement. But to me, I don't care about the order. So all this is treated as one way. So I have to count how many of them. So how many ways that you can arrange the R objects? R factorial ways. So this R factorial to me is just one way to select this R object. So I have to divide it by R factorial. So that's how you arrive at this. All right? Now let me show you in this example. 4 letters, A, B, C, D. Take 3 at a time. All right? So these are the, okay. If I choose A, B, C, so these are the arrangement. All right? Remember? Choose 4 factorial, divide by, taken 3 at a time. So you divide by 4 minus 3. See? All right? So, okay. So N minus R factorial. So there are four ways. Right? So A, B, C, A, B, D. Okay. So altogether there are 4. Altogether there are 24 4 factorial arrangement. All right. We only need 3 of them. We select 3 out of it. All right. So altogether it can be A, B, C, A, B, D, A, C, D, and B, C, D. And then if you choose this A, B, C, you have to arrange them. A, B, C, A, C, B. So this is the arrangement that you have. All right. But to me, I don't care about the order, how you arrange it. I just need 1. So I have to divide it by 6. All right. 3 factorial. So divide by 3 factorial to get the number of possible combinations. All right. So the number of ways to choose out of N objects is n factorial over n minus r factorial over r factorial. So this is how to derive the formula. All right. So n, choose r from n is defined as this. All right. Now, this is a little bit mathematical, but it's quite interesting. You know what is binomial? You know what is bi? 2, right? Binomial means that we are considering two things. So basically, we are considering the coefficients of expansion of this, right? You know a plus b squared is a squared plus 2ab plus b squared. A plus b cubed is a cubed plus 3a squared b plus 3a plus b cubed. All right? Now, yeah, you can work on for 2, 3, power 2, power 3, power 4 is okay. How about 10? How to write it down? What's the coefficients? So we just apply this, what we just discussed, called this, how to choose things. You can think of it. You have, okay, let's do it this way. Consider a plus b to power 10. What is the coefficient for a to power 6, b to power what? What should this? Can I have this one? Why cannot? And you expand it. Each factor you have to take either a or b. So the number of a's and b's in your product has to add up equal to this number. So this must be 10 minus 6, so it's 4. So what is the coefficient of this one? So it's very simple. You think of it, you have 10 boxes. 10 boxes. All right? So now that means you have 10 objects. So I just pick out of these 10 boxes, take 6 boxes. How many ways I can choose these 6 boxes out of 10 boxes? Whenever I choose that box, I pick an A. The box inside it has either A or B. So once I choose that box, I take the A. The remaining boxes, I take B. Multiply them together. That will give me A to power 6, B times B to power 4. So how many ways that I can choose the boxes? So I just have to choose 6 boxes out of 10 boxes. That is the coefficient. 6 out of 10. So the coefficient is to choose 6 out of 10. 10 is the number here, and 6 is the required one. Of course, you can consider, right, 10 boxes, right? I don't choose 6. I choose 4. Whatever I choose, the boxes I choose, I pick a B. The rest I choose an A. So that's the number of ways that I choose 4 boxes out of 10 boxes. How many ways? It's the same thing as 10, choose 6 out of 10. So that is this criteria. All right? Of course, you can prove it algebraically, but from probability or combinatorial point of view, the first one on the left-hand side, it means that you choose R out of n objects, R boxes out of n boxes. It's the same as you choose n minus R boxes out of n boxes. It's the same thing. All right? Same thing. Right? And the second one is a little bit tricky. On the left-hand side is to choose R boxes out of n boxes. So, of course, you can, if your algebra is good, do expand it and then do cancellation, you will get it. All right. And by the way, if you ask to prove algebraically, usually you should start from the more complicated expression, which means on the right-hand side, the sum of the two terms. Try to simplify it to get to the expression on the left-hand side. All right. Because this is more complicated. All right. All right. Simplify it to get to the right-hand side expression. But I have a combinatorial argument. Think of it like this. I have n objects, all right? I divide it into two groups. First one, I take a particular one, all right? A particular one, all right? This one must be in my choice. I want to choose R. So this guy must be there. So that I have to choose from the remaining n minus 1, I have to pick R minus 1. So I form R objects. R objects. So it's like I have n boxes. So okay, this box 3, I need it to be in my choice. So I take out this box 3, elements from the box 3. So the remaining n minus 1, I have to choose R minus 1. But that's not the complete story. So the next one is that, okay, now this guy, this box 3, or this particular object, is not there, not in my choice. All right? So in that case, I choose the rest choose R objects from this remaining n minus 1. So what I'm saying is that, okay, what I'm trying to say is that, okay, I divide it into two groups, n minus 1 and 1. So this one not in my R objects. So the remaining R objects must be taken from the remaining n minus 1 objects. While the other one is that particular objects must be in my choice of R objects. Then I choose the rest, R minus 1, from the remaining n minus 1. So there's two scenarios. The first one is the particular object is not in my choice. The second scenario is, yes, that one must be in my choice. So these two add up will be the same as I choose R objects out of the n objects. All right? So this is a probability or combinatorial argument. All right? But of course, algebraically, you can show that they are the same. The last one, when R is less than 0 or R is bigger than 1, this binomial coefficient is not defined. Think of it, how can you have the coefficient which is like you have a to power 11 times b whatever that you have here. There's no way that you can get it from 10, all right? You only have 10 factors. Each one you choose a, you get a to power 10. You won't get a to power 11. So that's what it means, all right? Okay, I think it's time. Okay, so I think I stop here and continue next week on the examples on this combinatorics thing. I'm going to upload the upload the second part of chapter 1 within this week, all right? And for those who are watching the webcast, please come. It seems that my attendance dropped.
Can you also upload the lecture slides and the webcast for group 1?
No, the webcast, no.
Then what about the lecture slides?
What lecture slide?
Like all these slides.
Oh, the slides already. The
It's not that popular.
oh, group 1
Yeah.
No, cannot access to group 1. You only can access group 2. You find your ways. Okay, webcast, no. Other groups lecture notes you ask, you find your own ways. You can only access. Those notes are only accessible to those students registered for that group. All right, so you find your own way.
Oh yeah, so just like you were talking about this, right? Is it 5 factorial?
Yeah, 5 factorial 5. Yeah.
So you say there's two ways, right? How come don't need to?
Yeah, times 2.
Oh, so you need times 2 lah.
Yeah, add them together.
2 times 5 factorial 5 lah.
5 factorial square. Yeah, correct.
Oh, okay.
Right? 5 factorial times 5 factorial is only the arrangement for a particular way to arrange the seats. All right. You have to fill the boys and girls in the seats. So there are two arrangements. So you have to add them together.
So this one is varies depending on the number of ways to arrange it. So it can increase. But for this case, two.
No, in fact, it's no way. This either must be different by one.
Oh.
Right? It's different by two, this number, then you can arrange them.
Oh.
That's why I'm trying to tell you, four boys and 6 girls, no way that you can
Oh,
arrange.
so it's either this or the same number.
Yes.
Oh, okay.
Right? Yeah. The same number one, there are two scenarios. So it's whether start with the boy or start with the girl from one end. All right? So there are two different ways. So that's why you have to add them together. Okay. Basically, $5 times 5 you have to add another $5 times 5.
Okay, thank you.
Welcome. Yes?
This one is the binomial